Okay, so today we are going to solve some example problems. The first, we are going to start with the quiz problem. We are going to solve the quiz problems first. And then what we do is that I will give you an example problem from chapter 3. And I will give you like 5-10 minutes to go over it and try to solve it. And I will answer any questions you may have, and then we'll try to solve it together. Okay? Is there any questions about anything? No? Okay. So let's solve the quiz problem first. So you had 2 problems on your quiz, and we want to solve all of them. What is this? Okay, problem. The first one was a shock wave. It says a 2-dimensional projectile with a sharp nose is exposed to a Mach 3 flow. So we have a Mach 3 flow coming in. And it is a 2-dimensional projectile. And we are assuming that we know the P1. We are asked to calculate the pressure ratio, P2 over P1, P3 over P1. So P2 is the pressure on the top surface, P3 is the pressure on the bottom surface. We have P1 here, also at the back plate, the back surface. We also have P1. And the last part is that we are asked to find the drag coefficient. Q1, that's C. And this length here is your C. Okay, so is there any ideas, or do you want to guys jump in and tell me how you solve this problem?
To find the pressure ratios, you have to use the theta beta Mach table.
Okay, exactly. So the first thing you want to do is to go to the theta beta M table. We also have these angles. This is 5 degrees, this is 10 degrees, right? Is there anyone who doesn't know what this table is, the theta beta M? So we all know what the table is. Essentially, it's not a table, it's a diagram, figure, whatever, plot. That looks like this. For each Mach number, these lines belong to different Mach numbers, M1, M2, and M3. And then for these, you can give the theta and find the beta from the diagram, right? And this diagram is in the book. It is also in my presentations. If you don't have it, you can also Google it, because everything is online and all of the problems are open book. So you can always use Google to give you the calculations for the theta beta. So if you do so, we have theta, Mach 3, theta on the top, let's call it theta 2, is 5 degrees, right? If you go to the theta beta, if you use the theta beta M relationship, your beta will end up being 23 degrees. Something I forgot to mention before that, this is obviously the reason we can use this theta beta M relationship is because we are assuming that we will have oblique shock wave formation on this, right? Otherwise, if we didn't have the shock formation, then the theta beta M relationship would have been meaningless, right? But why do we have the shock formation on this object? Is there anyone who can tell me that? Let's go with Josh. Yeah, supersonic, exactly. That's pretty simple, right? Pardon me? Yeah. Yeah. Okay, so oblique shock wave, we have to calculate the normal component of the shock wave, right? Using the M1 sine of beta equation, right? We have beta, we have M1. So 3 multiplied by sine of 23 is going to be equal to 1.172. This is the Mach number, the normal component of Mach number, downstream the shock wave. But the idea was we can take this, we can use the normal shock tables, right? Which I have here. Okay, it doesn't work. But you know where it is, hopefully. It is in the appendices, right? Is there anyone who doesn't know where to look for the normal shock tables? Okay, that's good. Because if you don't, that means you have not done well in your quiz.
Will we be using the appendices a lot in the upcoming chapters, and should we just print them out?
I don't know if you want to. I mean, if you like to print them out, why not? We will use them. Not a lot, but the thing is, all of your exams are online and open book, so you're not gonna have this type of settings for your final exam. You will be sitting at your home, so with your laptop. But if you want to, I usually do better with a printed thing. That's why I print everything.
I just want to know how much we'll be using the sense of printing out one using for one chapter.
Not much. I don't know, like 50% of the class, like 40%. I would say your best bet is for one of you to print them out and just share it. If you saw that you're gonna need them more often, you can print them individually. Yeah, that's the best answer I can give to you. Okay, so we use the normal shock. We use the normal shock tables. To find the normal component of the Mach number after the shock wave, right? So if you do that, if you go to those tables, you can get this value for the normal component of shock wave, and we can also find the pressure ratio. Okay. We can do the same thing for the M2 and yeah. So we have the pressure ratio, but we don't have the Mach number. This is just a normal component of Mach number. You have to be mindful of that. Okay. We can do the same thing for P3 over P1, which is part B of the equation. We have M1 equals to 3, and your theta is then. We also have the formation of the shock wave, an oblique shock wave on the lower surface. Okay, so we can do the same thing. We can calculate the normal components of the shock wave on the lower surface of the Mach number on the lower surface. So on the lower surface before the shock wave, it's going to be 3 multiplied by beta. So we have to find beta first. That's all this first. Beta from theta beta M relationship, or the figure, is going to be 27.5 degrees, right? Plug this in here. The normal component of the shock wave on the lower surface is going to be, the normal component of Mach number on the lower surface is going to be 1.385. Normal shock tables again. the normal component of the Mach number, the flow, after the shock wave is going to be 0.7483, and P3 over P1 is going to be 2.055. So we have the answer to part B and part B, A of the problem. And then the part C, which is the like toughest part of this question. So how can we approach this? Or let's actually do this. Let's go one by one and see what you guys did in your quiz. Okay? Let's start from the other side of the class this time. Let's start with Tyler. What did you do?
I don't think I solved this part.
You didn't solve it. That's all right. What about Anna Victoria?
I wasn't sure how to solve it, but what I did was, I'm trying to find it. I tried to sketch it out, and I tried to see, because it said that not every part of the pressure was contributing to the drag. So then I tried to think, well, if the drag was going that way, I tried to find the pressure component of the drag.
Okay.
What I found was like sine of 5 degrees times P2 and sine of 10 degrees times P3. And I thought that the P1 was working against the drag. It's going the other way.
Okay.
And
That
that's till where I got it.
okay, that makes sense. Okay, so is there anyone else? What did you do, Ryan?
I found the length of each side using like the sine and cosine relationships. And I found like the component that each pressure's, the drag component that each pressure is doing to each side, and then you have to take into account that P2 and P3 are acting this way, then the pressure pressure of one is acting the other way. Find the length and then just subtract them.
Okay. What about you, Nilla?
No, I don't know.
You don't remember? That's all right.
Basically what I did.
That's basically what it is. So essentially, the first assumption you made, which is the correct assumption, is the pressure force is the only contributing force to the drag. So that's the first assumption. We are not talking about the shear forces. We are not talking about the friction. We are not talking about any other types of drag. We are talking about the drag by pressure, right? So the pressure, if you want to sketch the pressure distribution, it will look like this. You will have P2, right, on the top, P3 on the bottom, and P1 this way. The main question you want to answer before moving on is what is the direction of drag? Essentially dragging your object, right? What is the direction of drag? To the right. To your right or to my left. To my right as well. To the right, right? So we are dealing with a two-dimensional object, so we are dealing with the drag per unit length, d prime. Okay? I'm going to calculate this force. So essentially, we are only interested in the projections of P2, P1, and P3 in this direction. Let's call it in the x direction. X, y. Okay. And these are the only parts that we are really interested in. We have the theta here. Let's call it theta 2. Let's call this theta 3. Okay. So we have P1. If you divide this object to two objects, I just want to write the list essentially. You have the contribution of P1 to this part of the object and the contribution of P1 to this part of the object. So, and we also have the projections of P3 that is being applied to the lower surface and projections of P2 that is being applied to the upper surface. So let's call this part P1 prime. Let's call this P1 double prime, which both of them are essentially P1 multiplied by this length and this length, right? Pretty simple. We're talking about forces here. So pressure multiplied by the area, which in this case is just a length because we are dealing with unit length in the depth direction, unit depth, if you will. And the same discussion here, let's call this P2 prime and P3 prime. So your total forces, your drag force is going to be P2 prime, right? The same direction of the drag force, minus P1 prime plus P3 prime minus P1 double prime, right? Double prime here, and that's it. Which all of these are essentially the pressures multiplied by this length. But what is this length? You can use the sine and cosine functions to find this length. We have, it is getting a little busy here, so I'm going to use a different color. We have this length, which is C. Okay, D prime is equals. So your D prime is essentially going to be equals to this length, right? And we have this theta. If you recall from the tangent formula is going to be equals to this length, right? The length that you are interested in, divided by what? Let's call this L, divided by C, right? So the L that you are interested in is essentially equals to C tangent of theta. So your D prime is P2 prime multiplied by C tangent of theta minus P1 prime multiplied by C tangent of theta. What in this case is theta 2, right? We can factor this out. And then plus P prime minus P1 double prime. These are actually just the p's, not the primes. The primes refer to the forces. These are the pressure. So this prime is referring to the pressure force. Double prime referring to the pressure force. But here we are only dealing with pressures. And multiplied by C tangent of theta 3. Does this make sense? Okay. So what else do we have to calculate? We have to calculate the dynamic pressure. What was the formula for dynamic pressure as a function of P and M? We already should have this formula, right? The general main formula is rho 1 V1 squared, but we can play with this formula and transform it to this function, P1 M1 squared, okay? In which we have P and M, right? So we don't need to calculate density or anything else. And what else do we need? We also need C, which we already have, right? So your CD is going to be equal to P2 minus P1 tangent of theta 2 plus P3 minus P1 tangent of theta 3. Okay, and we have already taken the C out, multiplied by C over gamma over 2 P1 M1 squared multiplied by C. So the C can cancel out. And we can play with this a little bit. We can actually divide P2 minus P1 by P1 here, right? We can do the same thing for the P3 minus P1 by P1, right? If you play with this a little bit, this is the formula you're gonna get for your drag coefficient, right? can bring these two to the numerator, right? We can have 2 tangents of theta 2, tangent of theta 2 over m1 squared multiplied by p2 over p1, which we already have, minus 1, right? p1 over p1, plus 2 tangents of theta 3 over m1 squared, gamma, I forgot the gamma, gamma m1 squared, multiplied by p3 over p1 minus 1. So p3 divided by p1 divided by p1 is going to be 1. Okay, is this clear?
What is the term in the second part, gamma m1 squared?
Gamma m1 squared, yeah. So we have the pressure ratios. We have gamma, we have m1. We can plug in all the numbers. If you plug in all the numbers, your CD is going to be equals to 0.03589. So, any questions so far? Okay, question number 2. It is telling us the air enters a frictionless constant area pipe. So something like this. At P1 equals to 60 psia. Okay, and T1 is 500 degrees Rankine. And M1 is 0.6. And it is also telling us that the heat is transferred to this pipe at this rate. Q equals to 300 BTU per pound mass of air. We are to calculate the exit Mach number. Let's call this ME. The static, let's call this M2 actually. M2. The static and total pressures and temperature at the exit. So P2, PT2, T2, and TT2. And also the critical heat flux Q star, at which we will thermally choke the pipe. Okay, and CP is, we can assume CP is 0.24 BTU per pound mass, degrees Rankine, and gamma is 1.4. Okay, so frictionless.
Was it given as Q star or just regular Q?
Any Q that can choke your flow is a Q star, right?
I don't remember it's.
But I can check the blackboard for you. So whenever you were asked to find a Q that is going to thermally choke the flow, you are asked to find a Q star. Okay, so it doesn't really.
Find the Q. Never mind. I got it. That's the question, not just given.
Pardon me?
No, you were given that. You were given the Q, but you're finding the Q star. I got it.
You were given the Q. Yeah, you were given the Q. You are finding the Q star. That's right. Okay. So, and it is a frictionless and it's also a constant area. So this time, let's just start from this side of the class. Let's start with Josh. How should we approach this problem?
pretty sure there was an equation to start off. I don't know, but it was related to Q and everything else. And then, find your QT. And then it was just a lot of ratios from isotropic and the Rayleigh tables.
Okay. Let's go to NearLab. How did you solve this?
Q equals CP delta T, and then Q is 300, CP is 0.24, T1 is 500, T2 is 1750 degrees Rankine, and I got P2 equals P1 times 1750 over 500, 1.4 over 0.4. P2 is 4812.78.
I don't want the numbers, just the procedure that you use. So for T, you use Q equals to
CP delta T.
CP delta T, right? And what is the temperature used here?
It's 500.
500. So you use the static temperature, right? You don't use the total temperature here. But we have a flow going in here, so this equation doesn't apply to the static pressure. This equation only applies to the total temperature, not pressure, right? Yes? Okay. So what did you do for pressures?
P2 equals P1 over, I got T2 over T1 to the gamma over gamma minus 1.
So use the isentropic relationships. Okay? So what else? Ryan, how did you approach this problem?
Well, since it's frictionless in constant area, you know it's a Rayleigh flow, and then I found to get the new exit Mach, I found the TT2, and then compared it to.
How did you find TT2?
Did the Q equation, but I used the total temperature. And
Okay.
I used the isotropic table to find that TT1 was 536 based on.
Okay.
So
That
what was the total temperature?
we'll get there. I will. The total temperature, the TT1, is actually 536, as Ryan mentioned. But I will explain to you. So, do you guys have any other things that you want to add? So, have you used the Ryan's procedure or the Josh or NearLab's procedure? Kind of a mix. Okay. Okay, so in general, in these type of questions, you don't need to use a lot of equations, right? Because you have the tables at your disposal, right? Yeah, that's a general. If you see that you are dealing with a lot of equations, a lot of complex equations, you are doing it wrong, right? Of course, if you can do that, but it will take you like a million years to answer this question. But let's just start here. We are dealing with Rayleigh flow. We have the static pressure and temperature, all right? And we are supposed to find the exit Mach number and the static and the total pressures at the exit. All of the exit parameters, so essentially. Okay. So what should we do? The first thing you want to do is to find the total temperature, because using that total temperature, you can find one of the parameters at the exit, which is your total temperature at the exit, TT2, essentially, right? How can we find the total temperature? We have the isentropic tables, right, for the Mach number. You can, of course, you can use the isentropic relationships as well that relates the Mach number to the temperature, right? If you recall, we had a temperature to the total temperature ratio that related it to the Mach number. It was a fairly simple equation compared to the other equations. But you don't need to. You can just use the isentropic tables that you have seen in the book, hopefully. So the temperature ratio for this Mach number using the isentropic tables is 1.0720. We have the static temperature, so we can find the total temperature at the inlet to be 536 degrees Rankine. Okay? And we want to find the TT2, right? Essentially, we can use this equation. Q is equals to Cp multiplied by TT2 minus TT1, right? We have the Cp, we have the Q. Cp is 0.24, and you have the TT1, 536. So your TT2 is going to be equal to 1786 degrees Rankine. So far we have one of the parameters of the exit. Okay, that's the total temperature. What is the next step though? That is, the next step is a make or break part for your solution. So if you do it wrong, the rest of the solution is going to be wrong.
I found the sonic total temperature at the end. Yeah, the sonic temperature at the end, and then compared the two to see if.
Exactly. So the first thing you want to do, that's the same thing we do for the friction flow, or the fan of flow. The first thing you want to do is to find whether your exit is thermally choked or not, right? To do so, you have to compare the sonic total temperature with the calculated total temperature you already have. And the reason we'll get that. Oh, what did I do? TT2 is equals to 1786 degrees Rankine. Okay, so let's do this. How can we find the total temperature ratio? This time we have to go to the right tables. And if you go to the Riley tables, you can find for this Mach number, you can find the total temperature to the sonic total temperature ratio, the inlet total temperature to the sonic total temperature ratio, which is 0.81892. Okay, you can either find the total sonic temperature to make the comparison, or you can find the inlet and outlet total temperature comparison, which this is what we have done. We can do both. You can do both, right? Or you can actually, what we have done is this. Doesn't matter which way you do, I just have the solution for this. You can actually find the ratio between the calculated total exit temperature and the sonic temperature, the sonic total temperature, right? How do we do that? It's pretty simple. You just add and multiply and divide by TT1, right? We have this ratio, and you have these two values, right? You can calculate the ratio. If you do this ratio, the ratio of TT2 over TT star is going to be 2.729, right? So what does this tell you? This tells you that this ratio is larger than 1, meaning that your exit total temperature is higher than the sonic total temperature, which tells you that this heat flux is going to choke this specific pipe, okay? So your flow is already thermally choked, right? Okay. So what should we do? Let's start. Let's go around the room and see what everyone has to say. Let's start with Josh.
Start with me again?
Yeah.
Let me see if I remember how I did this.
No, don't think of how you did this. Just think of what we have already done and what should we do. So we have decided that the flow is thermally choked, okay? Okay. What will happen, and the choking doesn't happen at the inlet because your total temperature at the outlet is larger than the sonic temperature for this flow, right? So the choking length, if you will, is smaller than if you were in a friction flow, in a fan of flow. The choking length would have been smaller than your total length, right? So what will happen to the flow?
Why don't you just adjust and you would have the knob
So
sonic axis.
So how does it adjust? Exactly. So what Anna Victoria is saying is that the flow will adjust in a way so you will have the sonic conditions at the outlet, right? But what is that mechanism? What is that adjustment mechanism?
You have the backflow with spillage, so when you're inlet around.
Exactly. Since we are dealing with the Mach numbers that are smaller than 1, right? So M1 is 0.6, right? You will have some flow spillage. This is how the adjustment goes, right? Which means that for this case, we have to calculate a new inlet condition, right? But what does stay the same? If you recall, for this type of flow, we said some of the parameters stay the same, right? So all of the other most of the parameters will be adjusted to new conditions, right? So that your outlet will be the sonic condition, right? But some of the parameters will just stay the same. What are those parameters? Do you understand my question? Okay. What are those parameters then?
Total temperature stays the same.
Total temperature, is that it?
And total pressure.
So we call the new condition the prime condition as always, right? And total pressure for the prime condition, which is the new condition. And the total temperature for the new condition is going to be stay the same, but it is not going to change. Okay. So which means that we already have the total temperature. What else you can say about let me put it this way. What can you say about the exit? What is there anything that is not going to change at the exit? At the outlet? Total
The total temperature also stays the same.
exactly. So we have already calculated TT2, which is going to become the TT star, let's call it T1 prime star, right? So the new sonic condition at the outlet. And we already have calculated that to be 1786. Okay, we can find this ratio, TT1 prime over TT1 prime star to be 0.3. So using this ratio, we can go to the Rayleigh table. Rayleigh table. Okay, which I think I should have open here. Yeah, this one I have open. Rayleigh table, T over T star, we have this parameter right here, which is 0.3, right? So we have to look for 0.3. So this value, the value for the Mach number is the 0.3 lies somewhere between these two lines, right? You can either do a guess or an interpolation to find the exit Mach number, which has to be a value between 0.24 and 0.28, right? For the Mach number. So your M1 prime is somewhere between 0.24 and 0.28. Right? Because my solution has a different value here. It's going to be between these two, right? Yeah. So let's say 0.25. Okay. Using the same analysis from the exact same table, we can find the pressure ratios. P1 prime over P star. Which I'm just going to copy whatever I have in my solution, but I think my solution has the wrong values, right?
You're looking at the wrong column.
This is the column we have to look at, right? Oh, total temperature. Yeah, you're right. Yeah, that's what. So that this is the, when coming to this table originally, we were talking about the total temperature ratio, not the temperature ratio, right? That was my mistake. So this is the value we're looking at. So Mach number is somewhere between 0.26 and 0.28, but is much closer to 0.28. So we're gonna just use the 0.28. Thank you. So we can have all the other ratios, P1 prime to P star, T1 prime to T star. It's going to be 0.36667. And we also can have the total pressure ratio.
How did you get M1 prime as 0.28?
Pardon me?
How did you get M1 prime as 0.28?
We just from this table, right? So we find the new T total, the total temperature ratio, right? Are you clear up until that point? 0.3? Okay.
From the total temperature ratio.
Yeah, you come here, it's 0.3, the closest to this one. The corresponding Mach number is 0.28. Okay, and we essentially wrote down all of the other corresponding values. Okay, that's it. But so the question is, the idea is your static temperature and static pressure have changed. Okay, right? How can we calculate the new prime values for inlets? Because we have new prime values for the inlet, right? How can we do that?
Using these ratios.
With these ratios?
Oh, those are total.
This is the ratio between the inlet and the outlet, right? We essentially have to find the ratio between the total and the static pressures and temperature, right? Because we have the total values, we don't have the static values. How do we find those total to static ratios? Isentropic tables. So we go back to the isentropic tables, right? For the new M1 prime, which is 0.28, you can find the P1 prime, PT1 prime to P1 prime, and TT1 prime to T1 prime. Okay. So this will give you 1.056, and this will give you 1.16. Okay, so we have these ratios, but do we have the total pressure and temperature? We calculated them, we found them earlier using the same isentropic tables, right? So here we only have done it for temperature, but we found them, you can do it for pressure as well, using the isentropic table for the original Mach number. Yeah, is this clear? Right? So you find these, you find the new corrected values. Okay? You have the corrected values, you have the ratios between the star conditions, a star condition between the star condition and the inlet condition, with the outlet and the inlet condition. These star conditions are your new outlet, right? So essentially plug and chug, you find the values for your final P2 condition. P2, T2, whatever you need. Is this clear? Okay. Then part C. We want to find the choking heat transfer rate. How should we find that? We are looking for the Q star. Total heat rate is, in general, total heat rate is going to be T minus TT, right? TT, the second condition minus first condition, right? Other than the second and first are, right? So essentially TT1 prime and TT1 star, right? The sonic, sorry, the star and the outlet and the inlet, right? You have the total temperature, you plug the values in. But what would you get if you plug the values in? What is the value you're going to get? 300, right? Because we did all of these calculations based on that, and we already know that that heat rate chokes your flow, right? And we had the flow split, so we had the adjustment, so this is going to be your choking heat transfer based on for the new flow. Does it choking heat rate for the new flow? Does this make sense?
So Q equals Q star?
Q equals here in this problem, because we already have the choking happen, your Q is going to be larger, your T2 is larger than the T star. That's, for this case, your Q is equals to Q star.
Is there any way to just determine that without having to go through all that?
Determine what?
Work just to get the same number.
Pardon me?
So you went through all those steps just to prove Q equals Q star?
No. We didn't go through all the steps to prove this. We wanted to find the pressures and everything else, right? So essentially, if you only wanted to find the Q, the only thing you really need to do is to find this ratio, and show that it is larger than 1, right? Which essentially meant that your flow is choked. Then you could have said my Q is going to be the same as the heat input. Q star is going to be the same as. Does it make sense? Okay. So is there any questions?
For that one, I don't know if this is right, but I just showed it. So using like the initial conditions, when we were like comparing the total temperature to the sonic temperature, I found the sonic temperature and then plug that in, assuming that the Mach stayed the same. Is that okay too? Like assuming it didn't reset, assuming that using that Mach number, it choked at the end.
But what was the value you got though?
Well, because I found that the choking temperature was like 650 something, so I plugged that in.
In the Q calculations?
Yeah.
But you cannot do that for the Q calculations, right? Because you have a flow coming. You have to use the total temperatures.
No, I did use total temperature.
Right?
The total, I found like the total sonic temperature that you compared with the total temperature you get, to assume then when you compare those temperatures, that's how you determine that the end would have to be choked. But assuming that like the flow didn't reset, I found the Q that would lead to choking at the end rather than.
So essentially you did it for a different pipe then, right?
I'm confusing myself.
We can talk about it after the class because I'm not sure if I understand your question. Let's talk about it after the class. Don't think about it then. Okay, so if there's no question about the quiz, we actually spend most of the time solving the quiz problem. Sure.
The step where you checked if the exit is thermally choked, so just kind of a stupid question, but is that something you should just go ahead and do for every problem, like regardless if it's really or Fano or anything?
Yes, exactly. So for the Fano flow, you compare the length, right? For the Riley flow, you compare the total temperature at the end, at the outlet,
Okay,
right?
and that'll be the same for any Rayleigh flow problem? Like
Yes,
you
yes,
always check
yes,
that?
yes. I mean, of course, it depends on the thing you want to find out at the end. You have to calculate, but I don't see a problem that you really don't need to do that in every problem, unless you are told that these are the exit conditions, right?
So this homework is gonna cover the quiz on Friday, right?
So the homework that I've already posted has some questions from chapter 2. Most of it is actually from chapter 2, like five questions from chapter 2. And I think 3 questions from chapter 3. So to be prepared for the quiz on Friday, make sure to solve the last problems first, right? Those are like the practice problems for the quiz. And then you'll get to the chapter 2 problems. Just after you take the quiz.
And this quiz is gonna be one problem or 2 problems?
One problem. So all of the quizzes from now on are gonna be one problem. Okay, and we are gonna have quiz each. You were in the class when we discussed this, right?
Yeah, I'm just going over again.
Yeah, yeah. So we will have one quiz each week, 1 hour quiz, and I may give you 2 questions at one of the quizzes, but it will be like an explanatory problem. You have to explain a phenomena, something like that. You don't have to do any calculus. So if you get 2 or more questions, it will be just an explanatory
Will
quiz.
you post the solutions to the homework or no?
I will post the solution to the homework after the deadline. The homework deadline, yeah. So, but if you had a question about the homework, you can always talk to me. If you didn't, have you gone over the homework? Have you seen the homework yet?
Yeah, I've done a couple of problems. I haven't got to the end.
Okay. What is there anyone else who has looked at the chapter 3 problems of the homework? So if you, I think you can corroborate whatever I want to say right now is that if you look at the chapter 3 problems, they are pretty straightforward problems. You just plug and chug. There's just one first step that you have to figure out, and then the rest of it you just have to plug in the numbers and use the equations. As long as you understand the equations, I don't see how you can get confused. Like the Riley flow problem, I understand there may be confusions, but for this chapter 3, it's going to be straightforward, right? So if you got into a problem, but you are always welcome to send me an email. We can set an appointment and meet, right? Today's Wednesday, right? We are meeting anyways tomorrow for your class, right? So you can have any questions, you can ask any questions if you have, and I will also be available on Friday and throughout the weekend through Skype or Zoom or whatever. Okay, so if there's no questions about the quiz, and we are going to start working on chapter 3 problems. I don't think we're going to have time to solve more than one problem, but this is essentially going to be very similar to your quiz problem. So if you understand this problem, you should be able to solve the problem. Okay, so let's do this. Let's see. Which one did we want to solve? 3.4. I'm not sure if it's the same problem as your homework. I don't remember. But I don't think no, it is not. Okay. So we are talking. I'm going to read the question for you. It is that's the problem 3.4 of the book. If you have the book with you, it is telling us a large bypass ratio turbofan engine. Bypass ratio. Engine, which is a JT9D engine from Pratt & Whitney that was developed in 1974, is described by its fan and core engine gas flow properties. In general, it is described by that. And then you have this. I wish I could show you on. Let me actually try to open this again and see what happens. It's a large block. Okay, let's see. Fluid impulse.
Did you buy the textbook?
I did. No, the PDF, no. But I did buy the original one, so.
Do you have to buy it, or does school buy it?
I mean, we are on the record, so yes, I have to buy it. Here. Yeah, so this is the question we want to work on. This is problem 3.4, as you can see here. This is the engine that you are supposed to work on. We are given the total pressure at different stages, right? And we also have the total temperature at different stages. This is actually what you usually get when you are dealing with one of these problems. We are also given the flow rates at sea level, takeoff thrust of like 43,500, right? Pounds. Your flow rate is 1248 pounds per second, and your fuel flow rate. One of them is the fuel. So this is the air flow rate. This is the fuel flow rate, right? This one is going to be 1248 and 248 pounds per second, right? And you don't need to solve the problem, just tell me which equations to use, right? The first part is asking us what is the overall pressure ratio of this engine. So what do you think we should do? And whoever makes the most contribution will get a bonus point. Do we have the pressures or not?
Those pressures increase in a pattern from 14.7 to 22.6 and so on.
But then you have a decrease here, right? You eventually, at the end of the course, you have to be able to calculate these pressures, right? That's the idea. But you will see, these are pretty simple relations. Usually isentropic relationships where you have the equations, but at this point you don't need to do it.
So the pressure of the propeller over the pressure of the turbine?
Pardon me?
I think this is the efficiency of it, but say it anyways. Pressure of the propeller over the pressure of the turbine.
Okay, that's the overall pressure ratio, which means that you want to calculate PT3, right, over PT2. Does this make sense? Can you do that? Can you take that ratio for me?
Say that again?
Can you take the ratio, PT3 over PT2? That's what you said, right?
Yeah,
You said pressure after the turbine. And that's after the turbine. Yeah. And the pressure at the inlet, right? So that's PT3 over PT2, right?
So 316 over 14.2.
21.5.
21.1, that's correct. So whenever you heard the overall pressure ratio, did I say pressure after turbine? Yeah, the pressure ratio of the jet engine is actually the pressure ratio of the compressor of the jet engine, because that's where the pressure ratio is the most important part, right? That's where you want to compress the air, right? That's where you want to be able to control the pressure ratio. So not the turbine, sorry, the compressor.
So it's before the combustor and the inlet?
Before the combustor and the inlet, yeah. How much you were able to compress the jet engine. Yeah. I'm sorry, I was thrown off. So whenever you hear the overall pressure ratio, you have to calculate the PT3, pressure after the compressor, and pressure before the inlet. Does this make sense? Mainly because that pressure ratio is the most important design pressure ratio, if you will, and that's actually where you want to be able to control the compression. Okay, so PT3 over PT2, which is 21.5. Okay, so let's go back to to the problem. Part B. Part B is asking us to estimate the fan gross thrust in pound force. So the fan gross thrust, how can we calculate the fan gross thrust?
We have the formula m dot naught plus m dot fuel times V9 plus P9 minus P naught times A.
But that is the jet gross thrust, though, right? We are looking for the fan gross thrust. So let me put it this way. That's actually this is a very good question to solve. These are actually the complexities of this problem, and maybe one of the shortcomings of the book, but they should have been more clear. So, like whenever you hear the term gross thrust, it means that the total energy generated, the maximum energy generated, right? We already have the equation for the jet engine gross thrust, right? Which minus the ram drag is going to give you the uninstalled thrust, right? But when you hear just one component's gross thrust, we are talking about the exit velocity of that multiplied by the mass flow rate that is coming out of it.
Do the installed plus the ram drag for the gross? Installed force plus the ram drag.
No. So whenever you hear the gross thrust, it is essentially the total force, the total thrust generated by each component. For the whole engine, is the pressure difference plus the m dot multiplied by the V exit, right? But for the fan, you have to look at the fan exit velocity multiplied by the exit mass flow rate of the fan. Does this make sense? Yes? Okay. Now the pressure change after the fan is negligible, so you wouldn't really care about that compared to the other pressures that we have. Compared to the other pressure changes, after, like the compressor pressure change, for example. So your gross fan thrust can be calculated I'm very glad that we started solving this problem. So m dot fan multiplied by the V that is coming out of the fan which if you go to this this figure here, the exit of the fan is this region, right? Which is region 19. Okay, it is just named region 19.
Does that include the top and the bottom, since there's multiple like, inlets and outlets?
Top and the bottom? What do you mean by top and the
Remember
bottom?
when we were talking
The
about
bypass ratio? What are you talking about the bypass?
Yeah, I remember when we were talking about like turbofans, they have multiple inlets and outlets. And
That's
different
right. That's right. It is exactly the same thing here. You have the bypass part here, and also the fan part here, right? But yeah, it does include all of it, and the velocities should be very close actually, depending on the diameter. But in this case, in this problem, we are only given one velocity, so that's the only thing we use. So we have the m dot fan, which is the m dot coming in, right? Multiplied by the velocity here.
Do we have the end up thing?
It is supposed to be your air coming in, right? M dot fan is the air that is coming in. That's the mass flow rate of air, right? What is the mass flow rate of air? $12.48. Okay, and what will happen if you multiply it by 1885? Okay, I think I'm making it because the nomenclature they are using here is
Why is
a
it W?
Pardon me?
Why is it W?
It's one of the old design things, so
I was getting confused and I saw the units and then.
now I have to make sure in the quiz problem that I fix these to the new comprehensible things. This actually that was just to make sure. When I was looking at this, my impression was this is air, this is fuel. But it's not the case. This is the bypass mass flow rate. This is your jet mass flow rate, right? And we are only given the velocity after the jet. So the gross fan here, the gross thrust fan here is only going to be the velocity after the jet multiplied by the mass flow rate after the fan. So can you do that calculation for me? Can you multiply 247 by 885?
Could you repeat that? The WAF and the
I will give you n dots, so you don't need to do it. You don't need to know this. And wherever you go in the industry nowadays, they will give you n dots. This is very old design, and they have just copied and pasted it. They shouldn't have done.
So for the fan gross thrust, it's WAP, it's the 247 times 885?
Okay, so yeah.
That's
Okay, that's-
218,595.
Pardon me?
247 times 885 is 218,595.
What was the final answer?
218,595.
Okay. Okay. Yeah.
Wait, so could you just clarify what values we're plugging in?
You are multiplying. So my goal here, let me actually be clear. My goal here is for you guys to know how to do this calculation, right? Not the values per se. So wherever you saw something like part B, you have to multiply but the m dot air by the velocity after the fan, right? The values themselves don't really matter, right? You will be given in any quiz, so I have to go back and look at the homework and to make sure that the values you are given are comprehensible. Because
But the air is the 247.
I thought the 247 was, so that,
You said the 247 was the fuel.
that's the jet. This is what I'm
Yeah,
confused.
that's why.
Doesn't
All I know is-
WAF mean after fan?
That's an F.
that's F, that W after fan. Okay, that makes sense.
But then what is log?
But then what is the AP?
After propeller.
After what?
After propeller.
After propeller.
Yeah.
But fan out.
There's a fan, no problem.
I'm looking up.
But like, so,
Okay, let's just go over the procedure for all of the parts of the problem, and then we'll go back, we'll have this discussion, right? Because this is not the point. We are clear on how to calculate the gross fan thrust, right? How would you calculate the gross compressor thrust?
so wouldn't the compressor thrust be the 247 by the 885? 'Cause now
You're looking at the values, Josh. Listen to me. I want you to give me the equations.
Would you do
Oh, it's just
the
mass flow rate times the velocity.
of the
Okay.
compressor?
Mass flow rate after the compressor times the velocity. Okay. That is the gross thrust, right?
And you said the pressures are negligible?
Are the pressures negligible after the compressor?
No.
No. Okay. So you have to include. So essentially, whenever you are dealing with the gross thrust, you are calculating the gross energy that is being produced in the direction of the thrust, right? That's the gross energy without accounting for any. Hey,
Morning.
morning. How are you?
Oh, you still got class going?
Yeah, just sorry, like 2-3 minutes. Okay. Yeah, that's why I wanted to make sure we are wrapped up.
Stared you dead in the eye.
Pardon me?
Stared you dead in the eyes. Stared you dead in the eyes.
Yeah.
Can you just call the solution on Blackboard?
I will. So yes, I will. Let's do this then. Let's stop here because I'm a little confused myself. I should have.
So what's the curve gonna look like on this quiz?
Pardon me?
What's the curve gonna look like on this quiz?
What is the curve? Which quiz? The first one or the second one?
This one.
This one is fine. You just gotta figure out how to do the problem.
It seems easier than the last
You do all
one.
of the fun problems.
It is definitely easier than the last one, but I think the authors of this book didn't really care about the comprehension